Okay, let's take a look at the other part of radicals, which is going to be solving radical equations. We can see right here that we have the steps for solving the equations. We need to state the domain restrictions, which we're going to pull from whatever is inside the radical, remembering that if I have a square root, I can't have a negative square root. Alright, I'm going to isolate the radical. I'm going to square both sides of the equation. And then once I've squared both sides, it should eliminate the radical. And then I can just solve for whatever the values of x would be. And the last part, which is going to be really, really important, is I always need to verify the solution, because we're going to come up with some possibilities when we square it that don't actually work, and I'll get deeper into that once we get to there. Alright, so for example 1, for the first one, well, all I have inside the radical is just x, which means that x has to be greater than or equal to 0 in order for this to be mathematically possible. Then what I'm going to do is I'm going to divide both sides by 3 and say the square root of x is equal to 5 over 3. And now that my radical is by itself, I'm going to square both sides. So when I'm squaring both sides, I'm going to put brackets around both sides to square it, to make sure that I square everything out properly. It's going to be more complex if I'm dealing with a binomial. When I take the square root of x squared, I just have x. When I take 5 over 3 squared, I'm going to have 25 over 9. Then I just need to actually verify it to say, well, can I prove that this is true? So put my solution back into the original problem. If I have 3 and the square root of 25 over 9 is equal to 5, then I'm going to say that 3 times 5 over 3 is going to equal 5, and 3 times 5 is 15 divided by 3, 5 is equal to 5, and that is in fact my solution. For the second one, it has cube root. Well, if I am doing a cube roots can be positive or negative, which means that I'm just going to say xer. There is not a limitation to what the domain can be. And then I'm going to do the same process I did last time. I'm going to have the 4, and I'm going to have the cube root of 8x. Well, in this case, I'm not going to square to get rid of the radical. I'm going to cube both sides to get rid of the radical logically, because it's a cube root. So I'm going to do the same thing I did before. I'm going to put brackets around this side and say I'm going to cube it, brackets around this side and say I'm going to cube it, and I'm going to get 64 is equal to 8x. When I divide both sides by 8, then I'm going to get 8 is equal to x. And once again, I'm just going to verify that that actually works. 4 is equal to the cube root of 8 times 8, or 4 is equal to the cube root of 64, and the cube root of 64 is 4, and everything is working. Alright, once we get to C and D, that's where we actually start to see some of these binomials. So here I can see that everything inside the radical that's going to give me my restriction is going to be 2x minus 3, which means that 2x minus 3 has to be greater than or equal to 0. So 2x has to be greater than or equal to 3, or x has to be greater than or equal to 3 over 2. There's my restriction. Now I'm going to go back to my equation, and I'm going to start by subtracting 3 from both sides to get the radical by itself. And I'm going to say the square root of 2x minus 3 is equal to 9. Now that the radical is by itself, I'm going to square both sides. And I can say that 2x minus 3 is equal to 81. I'm going to add 3 to both sides. 2x is equal to 84. And I'm going to divide both sides by 2. X is equal to 42. Then I'm going to verify that this works. So I'm going to state that if I have 3 plus the square root of 2 times 42 minus 3 is equal to 12, then 3 plus the square root of 84 minus 3 is equal to 12, 3 plus the square root of 81 is equal to 12, or 3 plus 9 is equal to 12, and 12 does in fact equal 12. And I can see that it works. Alright, for example D, all that's inside the radical is just x plus 1. So if x plus 1 has to be greater than or equal to 0, x has to be greater than or equal to negative 1. I'm going to isolate the radical and say that the first thing I need to add 5 to both sides, so 4 and the square root of x plus 1 has to equal 8. Divide both sides by 4 to get the radical by itself. X plus 1 is equal to 2. I'm going to square both sides and state that x plus 1 is equal to 4, or x is equal to 3. And then I'm going to do my verification again. For my verification, I'm going to state that if 4 times 3 plus 1, square root of 3 plus 1, minus 5 is equal to 3, then 4 times the square root of 4 minus 5 is equal to 3, 4 times 2 minus 5 is equal to 3, or 8 minus 5 equals 3, which it does. And everything works. Okay. Let's take a look at the last two examples here. So now we have a unique case of we have two radicals. So what I'm actually going to do is, well, I'm still going to start by stating that because both of them are just the square root of x, x has to be greater than or equal to 0. That's all that's inside of square root. Then I'm going to move the square roots of x to one side. I'm going to move the constants to the other side. So I'm going to subtract 2 root x from both sides. And I'm going to add 4 to both sides. Which means that I'm actually just going to have the square root of x on one side, and I'm going to have 5 on the other side. Because I can combine them because they're like terms. They're both just the square root of x. Then I'm going to square both sides. And I'm going to state that x is equal to 25. Let's check if that actually works. If I have 3 times the square root of 25 minus 4, is that equal to 2 times the square root of 25 plus 1? I have 3 times 5 minus 4 is equal to 2 times 5 plus 1. 15 minus 4 is equal to 10 plus 1. And both sides equal 11. Alright, for example D, if 2x minus 1 has to be greater than or equal to 0, then 2x would be greater than or equal to 1, and x has to be greater than or equal to 1 over 2. And there's my restriction. I'm going to subtract 5 from both sides and say that the square root of 2x minus 1 has to equal negative 3. I'm going to square both sides, and I'm going to state that 2x minus 1 has to equal 9. 2x is going to equal 10, or x is going to equal 5. Let's check and see if this works. So, if the square root of 2 times 5 minus 1 plus 5 is equal to 2, then the square root of 10 minus 1 plus 5 is equal to 2, or the square root of 9 plus 5 is equal to 2, 3 plus 5 is equal to 2, 8 does not equal 2. That is not the solution, which means that in this case, there actually is no solution. The only solution that we could find when we multiplied it out was impossible. So like we see here, in the last example, a potential solution that is within the domain may not necessarily work in the original equation. For this reason, it's important to always verify your solutions. These are called extraneous roots, and they can occur when you square both sides of an equation. So, what it's saying is that when we squared both sides of the equation and we got rid of the radical, we created a mathematical impossibility. We created a case that did not actually exist when we squared it, because if you think of it this way, if I had a linear function or a linear equation, and then I wind up squaring that equation and wind up with x squared, it's going to change the way that the equation looks. The same thing happens when we have to square both sides for a radical. If you put the square root of x into your calculator, it's going to look something like this, where it looks like half of a parabola. When I square it, what I'm doing is I am artificially creating the other half of the parabola, even though it doesn't actually exist in my equation. And we can see that in this case, that's where that negative value for the parabola would have come from. So that's what we call extraneous roots.